With all the work we've done with exponents already, right? We did exponent or exponential growth and decay last time. We talked about exponent properties. Now we're going to work on graphing these. When we come back from break, we're going to talk about the inverse of exponentials, which are logs. That tends to be a little bit tricky because it's completely new to everybody in here. So everything we do with exponentials is going to make all that work with logs a little bit easier. And today, while we're graphing exponentials, we're really going to focus on kind of the main portion of it. When we come back from break, we're going to add to the graphs. Today, we're going to keep it fairly basic. So we're going to work towards graphing functions in the form of a times b to the power of x minus h plus k. But today, we're just going to focus on the a times b to the power of x. And with a lot of graphs, we can come up with rules for how we graph those. I'm going to actually push us to kind of make a table of values and plug things in and then just connect dots. I think that always is a way that we can graph any function if we don't remember rules. We're also going to remind ourselves about domain and range, and then can we decide whether or not something is exponential growth or decay, both from the graph and also from the equation. So let's jump right into it. So we want to graph 2 to the power of x. What I'm going to ask us to do is to pick 5 points. And for every single one today, we're going to use the x values of -2, -1, 0, 1, and 2. And that'll literally be the exact same 5 values for every graph I ask you to choose today. And I'll talk about why once we actually kind of piece this all together. So we're going to figure out what is f of -2. So that's 2 to the power of -2, which has us using an exponent property. If I have 2 to the power of -2, the negative exponent says, hey, this term needs to go down to the denominator, which makes the numerator 1, and this is 2 squared, which is 1/4. As a decimal, that's 0.25. Okay, so that's 1 point we'll plot, -2, 0.25. Then we have f of -1, very similar idea, where now it's 1 over 2 to the power of 1, which is 1/2, which is 0.5. So we're growing just a little bit from -2 to -1. Then f of 0, so 2 to the power of 0. Anything to the power of 0 is 1. So we've got 0, 1. And then we have 2 to the power of 1. That's a little bit more straightforward. That's just 2. And then once we get beyond, or the exponent starts to get bigger, the numbers are going to start increasing much quicker. Okay, if we needed to, we could even go beyond this and go all the way up to 3. We'd get 8. And all those. After that, we're not going to have any other points that fit on this graph. Now, a really important feature of just exponents in general is these negative exponents. And we kind of talked about this with the properties, but if we were to continue to add x values that are negative, like -3, -4, -5, -6, etc., all that we're going to keep doing is getting a smaller and smaller decimal, or one that is closer and closer to 0. Okay, and I don't want us to use calculators, but just to kind of prove that point, let's say I take 2 to the power of -4. Okay, that's a small decimal. If I keep going, 2 to the power of, let's say, -10. Okay, that's the calculator's way of doing scientific notation. That's 9.76 times 10 to the -4. So that'd be 0.0009765, etc. So as the exponents get more negative, we're just getting closer and closer to 0, but never actually touching or never actually getting to 0, which creates a horizontal asymptote, just like what we saw with our rational functions. Okay, so as we get more negative, the line's going to essentially touch 0, even though it's never actually there. And then it's going to always increase very quickly on the other side of our graph here. All right, so after coming up with the graph, know that every exponential function is going to have the horizontal asymptote. Today, that asymptote for every graph I ask you to do will be at 0. It's not going to move until we start adding in a horizontal and vertical shift. We're not doing that at all today. That's something we'll do when we come back from break, okay? next thing I want to talk about, how can we decide that this is growth or decay? In the equation, I talked about this last time. Okay, it's growth because b is greater than 1. Okay, when I say b, I'm referring to the base. The base is greater than 1. This represents growth. The graph I know is growth because as x is getting bigger, y is also getting bigger, right? It's going up really fast as we move to the right. Okay, so this is a growing function of a graph, and that'll always be the case. As x gets bigger, if y gets bigger, that's going to be exponential growth. So as you work through these and decide is it growth or decay, think about what is it about the equation. And again, it's always whether the base is greater than 1 or between 0 and 1. And then what about the graph shows that it's exponential growth? Okay, those are connections I want us to make. All right, now for domain and range. With domain, we've talked about this with graphs, and to me, the graphs make it a little bit easier because if I see this arrow going all the way left, that means that the domain is going all the way to negative infinity. And as I see this arrow on the right, even though it's pointing up, it's also pointing right. So it's also going to go to positive infinity. Now, I also want us to think about what this means. Remember that domain is a set of x values. And so when I think about what x values I can use in my equation, any number can be an exponent, right? I can have negative exponents. We did that. 0 can be an exponent. We dealt with that. Okay, positive numbers obviously can be exponents. So I also want us to make connections where we're getting the domain from and how that connects to our equation. Okay, and with the exponentials, we're just asking ourselves what numbers can be exponents. Everything can be an exponent. Okay, every single number. Now, with the range and the y values we get, we're limited, right? We're limited by the fact that no matter what exponent we plug in, I will never get 0, and I'm never going to get a negative y value. Okay, if I make the exponents negative, like I showed us on the calculator, it's just getting smaller and smaller and closer to 0. But it will never be negative, and it will also never be 0. At the same time, though, we're saying that our range gets infinitely close to 0. So we write it as 0 with an open bracket or an open parenthesis, saying that we get really, really close to 0, but never 100% of the way there. And then the y values are going to go all the way up to positive infinity. So it increases very quickly. So with every exponential function, the domain will be negative to positive infinity for exactly what I just said. Every number can be an exponent. For the range, we're limited by the asymptote, okay, and whether our exponential function increases. Actually, even if it decreases, that doesn't change it, but you are going to see some that actually reflect, and that might change what your range ends up being. Okay, any questions about getting values, whether it's growth or decay, domain or range? All right, well, let's look at the next one. And with the next one, it's almost the same equation. It's still 2 to the power of x, but now those values are getting multiplied by 2. Okay, so that's going to just change our graph slightly. And if you think back to first semester, we had a whole unit on transformations. Remember that this would be considered like the a value. That's our stretch or compression factor. Okay, so if this number is bigger than 1, we're taking this previous graph, and it's going to stretch it out vertically a little bit. We're not going to see that all that much because of how quickly these grow, but I do want us to kind of make those connections back to the transformations we did first semester. Regardless, we're going to go through this the exact same way. So -2, -1, 0, 1, and 2. And we're going to plug these in. Now we have to think about some order of operations. So 2 to the power of 2 times -2. Well, with order of operations, I have to deal with that exponent first. 2 to the power of -2 is 1/4. So this is 2 times 1/4, which is 1/2, or 0.5. Okay, multiplying those fractions gives me 2/4. 2/4 is 1/2. Then f of -1 is 2 times 2 to the power of -1. That's 2 times 1/2. 2 times 1/2 is 1. F to the power of 0, that's 2 times 2 to the power of 0, which is 2 times 1, which is 2. F of 1, 2 to the power of 2 times 1, so 2 times 2, which is 4. Okay, f of 2, 2 times 2 squared, which is 2 times 4, which is 8. Okay, so again, kind of making that connection back to transformations. If we look at the y values we got in our first graph, what's the difference between all these y values I got right here and the ones that we just came up with? There's one operation I can do to every single one of these to get the ones that I just came up with. What's that operation? What do I do to each y value up here? How do I go from 0.25 to 0.5, 0.5 to 1, 1 to 2, 2 to 4, 4 to 8? What am I doing? Somebody help me out, please. Grace? Multiplying by 2, right? That's that vertical stretch factor, okay, that this 2 is representing, saying that all of our y values are just growing by a factor of 2, okay? Graphing the points, it's going to look almost the same. We're at negative 2, I have 0.5. Negative 1, I've got 1, 0, 2, 1, 4, and 2, 8. So it just grows a little bit quicker. We still have the asymptote at 0. Again, every asymptote with graphs we do today will be at 0. It's not until we apply a vertical shift that we'll see something different. This again represents growth because the base is greater than 1. And as x is getting bigger, also is y. So this is exponential growth. Domain for every exponential is negative infinity to positive infinity. Again, every number can be an exponent. The range depends on where the asymptote is. Okay, once again, it's at 0. We use an open bracket because we don't get all the way to 0. We just get infinitely close. And then it goes all the way up to positive infinity. All right. Any questions there? All right, go and flip this over. And 2 more graphs. I'm just going to explain kind of what happens with now that this base is negative because we're going to have some negative exponents. And I'm going to have you all fill out this back side. And that'll be it for today. And then the last page is the assignment portion. We're only doing 6 graphs. All right, so we're still going to go with x and f to the power, or f of x. We're still going to use the exponents of negative 2, negative 1, 0, 1, and 2. Now, when I find f of negative 2 and have these negative exponents, okay, there are a few ways that we can view this. One, I could distribute the negative exponent to the 1 and to the 2. Why don't I do that? Okay, that's getting at some of our exponent properties. So this is really 1 to the power of negative 2 divided by 2 to the power of negative 2. Well, remember the negative exponent is saying, hey, that term needs to move places. So the 1 is going to move to the denominator, and now I can make it positive. The 2 is going to move to the numerator, and now I can make its exponent positive. So this is really 2 squared over 1 squared, or 4 over 1, which is 4. So I didn't need to actually distribute that negative 2 to all the exponents. In this case, it almost makes sense just to flip that base and now make the exponent positive, making it 2 squared. So really, what I'm trying to show us here is 1/2 to the power of negative 2 is equal to 2 to the power of 2, which is 4. And you know what? I'm going to have you all take it from there. See if you can figure out what 1/2 to the power of negative 1 is. Okay, once we get to the positive exponents, it should be a little bit more clear. And let's check in after graph 3. So let's do like 2 minutes to graph number 3. We'll check that before we jump into graph number 4. Again, identify growth or decay and domain and range. Checking with the y values first. Again, that negative exponent flips that base. 1/2 to the power of negative 1 is positive 2. I'm kind of showing out how I apply the properties to get to 2. Again, a lot of you that are maybe a little bit quicker to put all these properties together will know that when you see 1/2 to the negative 1, that's just 2. Anything to the power of 0 is 1. Then with the positive exponents, 1/2 to the power of 1, that's just going to stay as 1/2. 1/2 to the power of 2, you can view that as 1 squared over 2 squared, which is 1/4, or 1/2 times 1/2. However you get to 1/4, doesn't matter to me. But basically what we're seeing here is it's the same graph as 2 to the power of x, it's just been reflected across the y-axis there. And that's because of the base now being a fraction and being between 0 and 1, which is why in the equation I know that it's decay. Okay, because that base is between 0 and 1. Then the graph is showing me that it's decay because now as x gets bigger, y is getting smaller. Okay, so that's how we're always able to tell for the growth or decay. As x gets bigger, what is y doing? If y is getting smaller, it's decay. If y is getting bigger, it's growth. Domain for every exponential, negative to positive infinity. The range, same as what we've seen here, it's 0 to infinity. No matter what exponent we plug in, we will never get 0. We will never get a negative. And it just keeps going all the way to infinity. All right, questions there? All right, everyone do number 4 real quick. If you think about how we got graph of number 2, you could probably come up with the values for y on number 4 really quickly. But I'll work it out too. We'll check it. And then that's it for today. Fair. Again, if we make the connection back to transformations and how we can apply those, the base is the same, right? It's still 1/2 to the power of x. It's just that the 1/2 to the power of x is going to multiply by 3. So all I did to find my y values is I just went up to the y values I got in graph number 3 and just multiplied them by 3. 4 times 3 is 12, 2 times 3 is 6, 1 times 3 is 3, 1/2 times 3 is 3/2, 1/4 times 3 is 3/4. Again, if you need to work it all out and do order of operations, by all means do so. This is still decay because of that base being between 0 and 1. Domain is the same. And for today, the range is going to be the same as well. But know that the range is not the same for every exponential. It depends on where that horizontal asymptote is. All right, the last 6 graphs. I'm not going to have you turn this in. Why don't you just, I want you to work through these today. It's not something that needs to be turned in, but I want you to do the exact same thing. Make the table, identify growth or decay, and state domain and range. I will make an answer key so that way you can check your work with these, but know that this is not something I need turned in really ever. Okay, just work through it. Should be pretty quick.